Okay. Right. Now we do something a bit new. Next step in the reasoning. We introduce. I mentioned that we would do this in the previous session, just in a hand wavy way. What we're going to do now is we're going to apply perturbation theory to what we've just done. And remember from the previous chapter on perturbation theory, you use a parameter lambda, so we'll do just the same thing here. We will expand the Hamiltonian in terms of powers of lambda, so h0 plus lambda h1 plus lambda squared h2, the first order, second order corrections and so on. And we will expand the wave function psi also in terms of a power series in lambda, series of powers of lambda. So your psi RT would then be psi naught plus lambda psi 1 plus lambda squared psi 2 and so on. Okay, so let's do that. Now the equation that we got for AM dot, dAm by dt, that's quite general, right? That's a general equation for STDE, STDE, time-dependent equation for Schrödinger. So, so the various, and that implies that the various coefficients of the lambdas, the left-hand side and right-hand side, have to equal each other. Okay? Or if you bring everything over to the left-hand side and you have 0 on the right-hand side, it means that those coefficients, after you plug in the powers, the expressions involving powers of lambda for psi and for the Hamiltonian, those coefficients, they're the coefficients of the powers of lambda, lambda to the 1 plus another coefficient lambda to power 2 and so on. Those coefficients have to be 0, right? Because the right hand side is 0. Okay, so now homework, ask you to do this. Now your let's make the h dashed, the perturbing Hamiltonian, just lambda h dashed, right? So this then is, your h dashed is looked on as a first order correction to the Hamiltonian. Right? So the 0th order would be h naught, and the first order correction to the Hamiltonian is h bar. So h would be h naught plus lambda h dashed plus lambda squared h2, but we're not going to bother with h2. Don't need it. Okay, so we'll just talk about the first order correction in the Hamiltonian. Right, now similarly with the a's, so here's your power expansion, a sum of powers of lambda. Now again, we're not going to deal with the second order or above, just first order. Okay, so a0 plus lambda a1, and these are your first order correction terms for your a, and these a's, they in general depend on time. Okay. All right. Now, so plug this term for the a's into your equation plus circle. This. Okay. Plug that into this. Work it all out, and your HMN. Let's see what happens to that. Let's see. Well, let's do it for 0th order first. So it'd be like lambda to 0. In other words, here. So try and find what a to the an to the 0 comes. So plug this and plug that into your STDE. Equate. Bring everything over to the left hand side. You've got 0 on the right hand side. So all coefficients of lambda have to be 0. So the coefficient of lambda to power 0, which is 1, look at that one, and you'll find that a dot 0, when you differentiate that with respect to time, same with that, same with that. So when you look at the coefficient of the power of lambda to power 0, you will get this. I'll ask you to do that for homework. Okay. So in other words, when you differentiate the 0th term of your a, you get 0. And that's what you expect, right, if you think about it. Because the 0th, that's what you have when there's no perturbing Hamiltonian, when h dashed is 0. Okay? Well, when h dashed is 0, you've got a stationary system. All your coefficients, a's, are constant, they don't change. Right? That's sort of expected. So if you differentiate constants, you get 0. So this makes sense, right? Physically, mathematically, intuitively makes sense, right? So all these a0 are constant. Yeah, so that's what I'm just saying here. So when h dashed is 0, there's no perturbation. There's no time dependence, because remember the time dependence came in due to the perturbing Hamiltonian h dashed. But when that's 0, well, there's no time dependence. So you expect these to be constant. Right? So dA by dt, dA naught by dt is 0. Alright, okay, now do first order. And I should do that for homework. So here's what you get. So derive this also from homework. Remember, you plug that in, you plug that into your, you use this for your Hamiltonian, you use this for your A's, equate, well, if you bring everything to the left hand side, the coefficient of your lambda to power 1, so just lambda, the coefficient of lambda has to be 0. Okay? So you'll get this. So you do that for homework. Right? Now have a look at it. You've got, what have you got here? Now you've got an expression for this. The when you differentiate it, the dot, as usual, differentiate with respect to time. So dA1, your first order correction for the A's, your coefficients of your U's, is something of this. Now you use your plus circle, this equation, to get that, right, to derive this, and you're equating. Well, the coefficient of the lambda to power 1 is 0, and you'll get this, and that follows pretty readily from this. So do it for homework. Don't just take my word for it, or the textbook. Actually do it, so that you get that mechanical memory of calculating it, and you see, okay, that's so where it comes from, right? So you get this. Now. You have here now a differential equation. dA by dt is something or other in terms of other a's, but these are 0th order a's, right? 0. This is 1. Okay, so integrate both sides. If you integrate the differential, these two cancel each other, sort of. So you're just left with a1m. The a naught does not depend on time, so all this sort of comes outside the integral. Now it's h dashed, that does depend on time, so we're going to have to integrate this over time. This also depends on time, so you get this. Now perhaps I should spell out. Now that's also an important equation, so I've labelled it. But this time star circle. Right? So star circle identifies, labels this equation, which will be important for future sessions. Okay. Now notice the t dashed and dt dashed. Now it's a theorem in calculus. If you differentiate this integral, you will get this. You'll get that. Right? So going the other way, so if you take the integral of this, you'll get the integral from 0 to t. You'll get this whole integral expression. Okay, that's. I'm trying to remember, when did I do that in calculus? Maybe first year undergrad. Okay. All right. Now you may have a question about the limits. How do you interpret that? Well, zero is what? That's interpreted to be at time. T dash is 0. That physically, that's when your perturbation starts. Right? Like in a sense, hypothetically, it switches on at time t0 is 0. Right? And that perturbation acts, is there, acting over time until time t. Right? So the perturbation is active, is working from time at 0 to time t. So a time interval of t, t minus 0. Okay? Now for some problems it depends on the context. You might have a limit here of minus infinity. It depends on the context. Okay? So that's how. So you've now got a formula, star circle, for the first order corrections in your A, depending on time, in terms of, well, several things. The 0th order A's, and an integral involving the mnth element of your permutation matrix times this exponential term here with the omega mn. And remember omega mn, that was the difference in energies, em minus en, the whole thing divided by, what was it, pi h bar. Okay? So we now have an expression for E1. And so we can calculate this, right, from here. Okay, so well, I'll just continue this analysis in the next session.